Good day, I'm Norman Wahlberger, and today we're going to address this very key problem of infinity in mathematics, which supposedly plays a big role, but actually doesn't really logically work. So it's time for us to face the music and expel infinity from mathematics, and return mathematics to a more modest, sensible, logical enterprise the way it used to be before the 20th century fantasy story got so overblown. So we need to return to the time when concrete computations were really what was required. We want to make computations that are concrete, that are down to earth, that we can actually complete and show people. And we want explicit examples that can be fully written down. Not just abstract stringing of phrases together, let such and such be the such when you do such and then you get such. But rather, have a look at this. Right? That's the kind of thing that we really want. And it means a very big change in our mentality, in our habits of thinking, in our approach to what we are doing here in mathematics. It's also time to reassert the crucial role of clear definitions and careful reasoning over the current axiomatic wishful thinking. We've gotten ourselves into a very big mess. It's time to actually acknowledge that and then to move forward. Okay? And the way to move forward is to go back to the importance, the all-importance of clear definitions. All the key words need to be very clearly specified and laid out. And there's no reason for postulating all kinds of things that we would like to be true without going through the work of actually proving them. That's not real mathematics. Now, in our last few videos, we've been talking about complexity and very big numbers. And we've seen that most of the numbers n from 1 to z, z being 10 triangle 10 plus 23, that means 10 to the 10 to the 10 to the 10, a tower of 10 tens plus 23. Most of the numbers, natural numbers from 1 to the z, have very big complexity. They have complexity bigger than 10 triangle 4. And we've seen that that means that they really cannot be expressed in our universe. These numbers are beyond us. It's then even questionable to what extent they exist. But now we'd like to turn our attention to not the numbers less than z, but the numbers bigger than z. And clearly the problems that we have from 1 to z are going to be considerably expanded upon when we go beyond z. Now any such number, such as say this one here, must have complexity less than 10 triangle 4 if they are to be visible. So if we're going to consider numbers bigger than z that we can actually see, that we can write down, that we can specify in some fashion or another, then their complexity has to be lower than this number so that it's possible to express them in our visible universe. And this makes them very, very special, because there are so few numbers, proportionally speaking, in this range, once we go past z, that have such hugely small complexities. The complexity of z is very small, but numbers like this are very special, they're sort of uncharacteristic, they're very singular anomalies in this sort of zoo of numbers that we're supposing are out there. And more to the point, there are at most 10 triangle 4 of them. Right? If we're going to consider numbers beyond z that we can actually write down, then they have to be, first of all, very special numbers, but moreover, there's actually a relatively small number of them. Relatively small, meaning less than this humongous number. But this is the number that we've seen is sort of supportable in the universe, even if we imagine ourselves writing at the Planck scale and using the entire universe. So there's only really a very constrained, finite number of them, especially when you consider we're talking about, vastly bigger numbers than this one. In particular, there's not an infinite number of numbers that you could actually write down. This should be well understood. I mean, it's kind of obvious if you think about things in a physically realistic way. In other words, if we take seriously what it is that the physicists, the astronomers are trying to tell us about the world in which we live in. And it's really collapsing this whole nonsense of infinite sets, right? I mean, the universe is a very big, but ultimately bounded kind of finite place. We don't know how big that bound is, but most physicists are pretty convinced that there's actually a limit to the world in which we live in. Therefore, a limit to the complexity and the size of the mathematical objects that we are able, even in principle, to consider. Now, of course, by modern 20th century mathematics standards, the idea that there are not infinite sets, there's not an infinite number of natural numbers, there's not an infinite number of anythings, in fact, is very heretical. It's going against a fundamental belief system which is enshrined and encoded in so much of 20th century mathematics. It will be very challenging for a lot of people who have been trained in this system, who have learned from an early age that all of mathematics, or at least very much of mathematics, is ultimately built on infinite sets here, infinite sets there, infinite functions there, infinite operators there, etc. Very significant mind change needs to be made. But we can, for example, look at the physical world and ask ourselves, are there any infinite things in our world? If we ask a physicist, for example, are there any infinitely long objects? Like, there's an object. It's not that long. You make it longer. Imagine, an object like this may be a kilometer long. Maybe we can imagine it 10 kilometers long. Maybe we can even imagine it 1,000 kilometers long. Maybe 1,000 light years long. Okay, it's starting to push the bounds. But is it possible to have an infinitely long object, perhaps like an infinitely long drumstick, in our world? Well, I think every lay person, whether they're a physicist or not, is going to say, well, of course not. It's ridiculous. It doesn't make any sense. Even the meaning of that phrase is questionable. How about infinitely heavy objects? Here, for example, is a marker. It's not too heavy. We can imagine it getting heavier. Or we can imagine changing the materials that it's made out of so it starts getting heavier. Okay, so let's imagine it's getting heavier. Oh, it's harder and harder to hold up. Now we imagine it getting heavier and heavier and heavier. Perhaps it eventually gets to be a ton. I can no longer hold it up. Then eventually it gets to be 1,000 tons. It goes crashing through the floor of my room. 1 trillion tons. Okay, maybe it's made out of some kind of black hole material. But is it possible to imagine that this is an infinitely heavy object? Can we let the weight go to infinity? Again, a physicist would say, of course not. The ordinary person on the street would say, of course not. That's just not possible. But that is the kind of thinking that mathematicians do all the time. They say, all right, we have something, we kind of understand it in a finite situation, let's go to infinity, and then we get some new kind of object that we can't actually see or write down or experience directly, but we can imagine it. How about an infinitely fast object? Maybe someone who can run 100 meters much faster than Usain Bolt. Maybe 100 meters in 1 second. Okay? Shoot a bullet, no problem. How about in 1 trillionth of a second? Okay, maybe a photon. Now, let's let the velocity go to infinity? Is there an object that can go infinitely fast? You start the race, and at the same time it's already at the finish line 100 meters down the road. Is that possible? No, right? Doesn't make any sense. It just doesn't exist. How about an infinite amount of time? As far as we know, doesn't make any sense. In fact, the meanings of each of these terms, one should understand, are already questionable. It's not clear what this even means. What does it mean to be infinitely long? What does it mean to be infinitely heavy? What does it mean to be infinitely fast? It's really not clear that these things are defined correctly, except just sort of by stringing words together. So I claim that in mathematics we face a similar situation as we do in the real world, that talk about infinitely large objects, infinitely large sets. Doesn't make any sense. Not only doesn't make any sense, but it's logically unnecessary to create beautiful mathematics that reflects the world that we live in. It's not necessary to have infinity. Now, there will be some defenders of infinity that will argue that what I'm saying may be very reasonable for the physical world, but it doesn't apply to the mathematical world because it's intrinsically different, that we're operating in an intellectual realm, in a perhaps even imaginary realm that's not necessarily connected with reality. So what we can do in reality doesn't necessarily correspond. And so they will say that even though we cannot exhibit infinite sets, we can think about them abstractly. In fact, logically, they may even assert that once you have the notion of a finite set, then the notion of an infinite set is just sort of complementary to it. A set which is not finite is infinite. It's a very common argument. Just look at all the sets, and then the ones which are not finite are necessarily infinite. Okay, that argument presupposes that you have a notion of sets which already includes things which are infinite. You know, yes, if we had a big pool of sets and some of them were finite and some of them were infinite, then yes, you could argue that the ones which are not finite are infinite. But we don't have such a pool of sets to begin with. We need to define the term infinite. It's not just all of the things which are not finite. That's a kind of grammatical construction, very common, but it doesn't really work. And let me illustrate that by looking at some other examples. There's lots of kind of concepts that you can, create at some level by taking a legitimate concept and then sticking a negation in front of it in some fashion or another. For example, how about an unstoppable mouse? Now, most mice can be stopped. You can put a wall in front of them and they can't go through the wall. You can put them in a box. You can stop them. Okay, so we have the notion of an stoppable mouse. Does it mean, therefore, that we have a notion of an unstoppable mouse? Is that a sort of a necessary sort of flip side to the concept? How about an invisible hotel? We can see lots of hotels which are visible. Does it mean that there are then invisible hotels? Because logically the fact that there's visible hotels means that there must be invisible ones? How about immovable kittens? Most kittens are movable. So can we postulate the existence of immovable kittens just by creating this grammatical expression? Or how about an incompressible mattress? Most mattresses are compressible. You can push them down a little bit. And so, stick this little in front of it, and suddenly we have a new concept. Are these really legitimate concepts? Well, you can ask yourself, well, are there any of these things? No, there aren't. Okay? The concepts are grammatical constructions, not really conceptual constructions. They're things that you get by just stringing certain words together, irrespective of whether they actually result in a proper definition. So many people will say, no, we can still imagine infinite sets. I may not be able to build one, but I can imagine it. The set of all natural numbers, I can imagine that set. And I claim that no, you cannot. What you can perhaps do is you can imagine that you can imagine an infinite set. That I'm willing to grant you. You can imagine that you can imagine an infinite set, but you can't actually imagine an infinite set. So the term infinite set is not the opposite of a finite set. What it is the unjustified expansion of a legitimate notion into a realm which is unsupported by direct experience. We're taking a concept which does make some sense and expanding it linguistically, grammatically, to an area where it doesn't really apply. Now I have a blog which I write in occasionally. The name is NJ Weilberger. That's actually the URL there. The blog's name is Tangential Thoughts, and most of the entries are connected some way or another with mathematics. And at the end of last year, I wrote a blog called A New Logical Principle. And this blog in particular I think is interesting because it introduces, first of all, some healthy skepticism towards the laws of logic. Okay? This idea that the laws of logic are not set in stone and that we can discuss and critique and debate what are the laws of logic. Okay? They're not given to us from on high. And it also introduces a new principle. I think it's a very important principle that has a lot to do with this discussion, and I want to introduce it to you. So here is my new logical principle, the law of logical honesty. It is, don't pretend that you can do something that you can't. Simple. Who can argue with that? That's what we're doing a lot of the time in current pure mathematics. Okay? And in particular, a very important example, don't pretend that you can put all the natural numbers into a box. That's what you're doing when you write down this. It's a pretending that you can do something that you demonstrably cannot do. We've seen the complexity when we get to bigger and bigger numbers. We've seen that things get very, very difficult to describe, and the number of numbers that we can actually write down starts to thin out more and more and eventually stops because of size limitations. And where exactly it stops, well, we don't know exactly. Right? It's not as if there's a biggest number and then we can get to that, but we can get no further. Rather, the job just gets more and more tougher. We slow down, and eventually the size of the problem overwhelms us long before we've gotten to the end of all the numbers. So to pretend that you can put all the natural numbers into this box and say, hey guys, I've got the set of natural numbers here now. That is a pretending. It's really a kind of intellectual fraud. Okay? And the law of logical honesty says, let's stop doing that, guys. Okay? Now, this is not some idle philosophical discussion. This is an argument that has enormous implications for modern pure mathematics. Huge consequences. In particular, it's a necessary consequence of understanding that there are no infinite things of any kind whatsoever. It's a necessary consequence to realize that most of these subjects, these topics in pure mathematics, essentially collapse logically. In their current form, they are just not self-supporting anymore. You pull the rug of the infinite delusion out, and they all sag in a very sad way. We're talking about analysis, topology, differential geometry, algebraic number theory, differential equations, measure theory, analytic number theory, Lie theory, certain parts of algebra. A lot of them really have very serious dependencies on infinite reasoning, and once we face the music with respect to the non-existence and nonsensical nature of infinite sets and other infinite things, then these subjects really become very tenuous logically. Combinatorics and some related disciplines remain largely unscathed. Okay? But a lot of mathematics really has to be rethought. So we have a huge amount of work to do here. Okay? It's a very, very big challenge, especially for you young people who are entering mathematics now. Don't underestimate the huge job that you are going to have to tackle. Because what I'm saying here will eventually be taken up by other people. Already there are people from computer science backgrounds and other backgrounds who are starting to think more sensibly about what's really going on. And the current belief system is just not sustainable for that much longer. Of course, it will be sustained just by habit and authority and people trying hard not to see what's going on. But ultimately, it really has to be changed. And you young people are going to have to do a lot of it. So there's a lot of work to be done, but it's very exciting because it means that we can transform these subjects. We can really make a big contribution here. Right? It's not the case that mathematics is set in stone and that you can only add a little bit. That's not the case at all. Okay? All of these subjects have to be rebuilt. Someone has to come along and take Lie theory and say, let's do it right. Let's start correctly and build it up in a very solid way. It hasn't been done. I know, I was a Lie theorist for a long time. Okay? And it's representing huge opportunities for young people. New directions. Very exciting, but scary at the same time. Now, there will be practitioners who will try to cling to the belief that small modifications will fix things. That we can just change the axioms, or that we can somehow patch up the real number system, or that we can sort of rephrase things without doing a lot of work. But believe me, that's not going to really be much more than a band-aid solution. Okay? Fundamentally, we have to rethink a lot of things that are going on. And in my channel here, you can see lots of evidence. You can see already I'm putting into place ways of thinking about different subjects. Pretty well all of my series more or less have this orientation underlying them. So you can see examples of how it's possible to do various subjects, or at least start doing various subjects in a more logical, finite, computational, concrete, down-to-earth, write-downable way. Okay? Feet on the floor. So, although many of these subjects will collapse, they can be rebuilt and they will be rebuilt. Okay? The result will be a stronger and more logical and more computationally useful mathematics. Once we put in the hard work of rethinking the foundations of all of these subjects, we will end up with a much more beautiful and much more powerful and much more useful mathematics. In the meantime, we don't need to just get rid of all of the mathematics that we've been doing. We don't have to say that these theorems are all wrong. Okay? What's better is to just think about importing these disciplines from pure maths temporarily into applied maths. In other words, to interpret the so-called theorems as actually not really theorems, but as approximate statements that have some legitimate meaning in the world of approximate statements. Okay? So it's not as if the things that have been discovered are no longer of value. They are still of value, but they will form the basis for a more precise and a logical new mathematics. But the current results can still be interpreted in an applied sense, and then, well, they can be processed and used much as we do already. In fact, that's already happening. I mean, computers take these subjects and take all these sort of ideal assertions involving infinite sets and real numbers and just strip all the infinities away from them anyway, convert all the real numbers to floating point, and work over here with basically applied sort of finite images of them. So that's effectively already what's happening from an applied point of view. Okay, so some interesting and controversial positions that we've mapped out today, right? Very much so. And it's a little bit saddening for me to have to be so negative, But on the other hand, it is necessary for me to give people a push, because if you don't give people a push, they're not going to move. They're quite happy where they are, doing their thing, just ignoring to a large extent the very serious logical problems, sort of minimizing them. But we want to go beyond that. We really want to move into a more happy framework for mathematics. In my next video, I want to return to big numbers and show you how to even get bigger numbers than we've got before, and that'll be some fun. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.